Hello, my name is Virginia Weston, and today we'll be discussing constant velocity motion. In this presentation, I will be explaining my process findings, comparing data, and discussing the fundamental principles behind this lab. So we had a few goals for this lab. We wanted to derive updated position and velocity formulas from Newton's second law, which can be found here. We also analyzed a video and tracker of an object moving in constant velocity, and we used GlowScript to create a computational model of predicted motion with the updated position and velocity formulas, with the assumption that initial velocity is equal to final velocity. And we found that when velocity is constant, the predicted model and the experimental model we made in tracker had little divergence because the overall net force is zero and velocity was constant. So here's some fundamental principles. We are able to convert Newton's second law into the momentum principle by substituting in momentum for mass times the change in velocity. And from the second formula here, we are able to derive that velocity update formula by separating the delta V and solving for VF. And we also have our updated position formula. So the object I used for the experiment was a disco ball, and here are the measurements that I specified in tracker. Here is a video of the ball moving from the origin, which I set it to be the center of mass, towards the left, which would be the negative x direction. Since the origin's at the center of the ball, the initial position is 0, 0, 0 meters. So I took the first two measurements of time and position to calculate the initial velocity and found that to be negative 0.72 meters per second. And then from the initial velocity that I recorded experimentally from tracker, I added that value into GlowScript as the initial velocity, and I changed the GlowScript code so that the model ran until the final time of the tracker model, which was 0.833 seconds. I also replaced the ball's velocity and position with updated formulas that we discussed earlier, and altered the time to be time plus delta t, so that way we could advance it and predict the final motion over and over and over again. So one of the most important aspects of constant velocity motion is that the net force of the object in motion is zero, and this means that the ball is not accelerating or decelerating and that the forces acting on it are balanced. And because it's in constant velocity, the initial velocity equals the final velocity, and because the mass is constant, we can say that the initial momentum also equals the final momentum, and because they're equal, if we subtract the final from the initial, also known as the change in momentum, it's going to come out to be zero, which would make the net force equal to zero because zero divided by anything comes out to be zero. And you can see here that GlowScript made this graph of velocity versus time, and it is just a constant line at negative 0.72 meters per second. So here is just a visual from GlowScript of the predicted position versus time in the form of a graph and a model. And then when we go to compare our results, you can see that there's a little bit of divergence in the graph, but very slight errors. And there's also outside forces that are being summed up to equal zero, and we cannot directly measure these forces. So that would be a limitation that would cause some divergence. If we changed the x-axis to be in the positive direction, the slope would stay the same, the magnitude of the vector would stay the same, but it's just going to go in the opposite direction. And you can see that this is now a positive slope compared to the negative slope we originally had here. And here is a graph of velocity versus time, and the red value is going to be the initial velocity going in the negative direction, and then the blue is going to be going in the positive direction, and you can see that it's the same value, just on opposite sides of the x-axis. Once again, if we have constant velocity, that means that the net force is equal to zero, and we have balanced forces that are acting on the ball. So in this diagram, I denoted the blue vector to be the normal force, which is going to be the ground that's pushing up against the system that keeps it falling into the earth. And then the red one is the weight, which is an equal length to the blue vector, which means that it's just staying still and canceling out in the y direction. And then in the x direction, since the ball is moving, we still have this driving force that's making it move, but it's going to be canceled out by perhaps like friction of the air or on the ground. And I made the magnitude of these two vectors added together the same magnitude as the green vectors, that way they all cancel out. But also there could be more forces involved, and these are just some general ones that I can considered. Just to summarize, we used the momentum principle and got that from Newton's second law, and from there we were able to predict motion of the disco ball with the computational model using the updated position and velocity formulas, and we found that those were pretty accurate when compared to the experimental data. But of course there are some discrepancies because of human error, and we're not totally able to measure which forces cancel out to make the net force equal to 0. Thank you.